Hello, my name is Andy Schweitzer, and this is a quick little video on introduction to setting up a titration. This one's generally geared towards an acid base titration, but it could be theoretically applied to any titration. First thing we have here is how do you physically set up the burette. Now, I have a picture right here, and probably the best picture I got. A few things you might want to notice. You have a beaker, you have the burette, stand holding the burette, you have a clamp holding your pH meter, room to drop it in there. A little bigger beaker might be the best case here as opposed to a small narrower one. A stir plate would be optional. Make sure that when you're stirring you're not whacking your pH meter. Okay. As far as the pH meter is concerned, a few things about the pH meter. One, they're vernier probes. So when you're putting it in here, the vernier probe looks like so, and it comes down, and it has a top with a little wire coming out, and it has a little cap with a little bottle that goes over the top of it. More than one student has, and again this is not a very good drawing, but more than one student, the pH meter extends inside here. More than one student has done their lab trying to leave the cover on, and of course you need to take the cover off. So when you take the cover off, it looks like this. And your little edges down here. Okay. And this thing is the part that you need to stick in the solution. I would use your water bottle and I would rinse it slightly before you put it in, and I would also rinse it before with your distilled water before you put it back into your solution. If you tip this over, make sure let me know when I will, or for some reason you don't have enough fluid in here, let me know and I will give you some, it's pH 4 buffer that this stuff sits in. Alright, so that's set up. Now the burette, a few things. One, this thing here, it numbers a little differently than kids sometimes think, so look at it carefully. This is called the stopcock or valve, and this is the tip here. Okay, a few things you want to do. You want to rinse. Okay, and to rinse this thing, you pour in a little bit of water, and you turn it sideways. And this is quite often demonstrated in class, but you turn it sideways, and you would roll it, pour it in, and you'd roll it out at the end, and feel you roll it around in a circle until it pours out the end. Okay, a couple times with water, and then more importantly, you want to rinse it with the actual chemical that you're putting in there. Whether it's acid with this base or some other chemical, you want to rinse it with that particular chemical. Then from there, you'd want to fill the burette. Now, you don't always have to fill it all the way to the top. Okay, usually it says it starts at 0 and it goes down usually to 50, although there are smaller burettes. The only reason why I really would fill to 0 is that if you're using our vernier software, if you're at 0, it works easier for dispensing the chemical and then initiating into the computer. What you would do with the computer, you type in the volume you've currently added, which would be 1, and then here if you're at like 15, it would be exactly what the number you're at. So if you went a little bit farther, let's say to 16.5, then you could really put in 16.5 into the computer. Okay. Either way, get it full, attach it in here. You don't have to, but I almost always put the known into the burette, and in the burette below, or in the beaker below, I have the unknown. That's not always the case, but usually I'm dispensing something of which I know what it is. Again, definitely not always the case. Alright, so that's how you set it up. You want a couple things. Make sure that this end is full before you start using it, because you're going to want to make sure this is accounted for. Don't have it empty, and then your first little bit when you open it, you fill that spot. That is assuming that this is full of your liquid. Okay. If you have a partner, one person can get this thing set up here, and one person can get the burette set up. Usually, again, we always try to run several trials at once so that you can titrate a few things right away before you get started. Okay. As you're measuring this thing, you'd want to make sure that your eye is looking at this thing all right, parallel. If you're short, well, do your best. Or have your partner help you out. Okay, that's pretty much it for setting it up and getting it started. Now, the actual setting up of the pH sensor, there is a short video on that for setting up the pH sensor, so you're going to want to watch that. Okay. How do you actually track the pH? Okay, well, there's two ways that you can track your pH. As you're adding in one substance into another, whether it's from burette, okay, and you're going to drop it into your beaker below, all right, you're looking for, you need to have some sort of visual change so that you know where you are adding your chemical to, or when you stop adding, and that is usually referred to as the equivalence point. Okay, now whether we're doing an oxidation reduction reaction or whether we're doing an acid-base reaction, we call it the equivalence point, where the moles of what you've added here are equal based on the stoichiometric ratio to what's in here, and that way you know what you have. But the older methods to track pH would be indicator. Now, I would say the most common indicator that you have is phenolphthalein. You know, it's a little bit difficult to spell, but it's one thing I can spell. And it is, in acids, it is clear, and in bases, it is pink. Now, it's not exactly right. If you tracked it, you'd see that it turns at about 8 pH. Okay, so it's not exactly right, but it's close. The other opportunity, there's lots of indicators that turn at different times. This one works good if you're looking for something that's changing around the pH of 8. Okay. But in this, other option would be to use a pH meter. Okay. Now, a pH meter is something that we are going to essentially track the pH, you know, straight up as it's happening. Okay, so you wouldn't want to be dropping the substance that you have right on the pH meter. You'd want to drop it in, stir it a little bit, and allow the computer to adjust to the new environment. There's a keep button, and then you can watch it change and hit the keep button and then type in your value. That's for the Veneer software. When you're tracking your pH meter, okay, and this thing is going to list out what you have. Now, every time that I start titrating with a pH meter, generally speaking, we're going to be taking multiple readings, and we're going to be graphing them. The whole purpose of the indicator or the pH meter is to find the equivalency point. Well, what happens is if we were titrating, let's say this is P, usually we have pH on one side, or it could be, well, we could have, it doesn't really matter, this would be moles of acid added, okay? And in this case, I'm going to call it a base added. We'll titrate into an acid. So we'll start out with a relatively low pH, and you'd be adding your particular acid in, okay, or your base into your acid. And therefore, in your beaker, when your pH meter is measuring this thing, it is measuring that this thing is in fact acidic. And as you add more and more of your acid or your base into your acid, you start to become a little bit more basic. Okay? When you approach this situation where all of your acid, okay, you have H plus ions in here. Okay. Your H plus ion, I'm going to give myself a little more room here. Your H plus ion is going to be reacting with your hydroxide ion to produce water, H2O. Let's go HOH. All right, this is a liquid, and therefore it just falls into, moves into the solution. All right, so now as you drop in your hydroxide, your concentration of your remaining acid starts getting less and less and less, but it is still acidic. Okay, so if you have your H plus ions in here and they're floating around in here, you're dropping in your hydroxides, and every time one hydroxide gets dropped in, it knocks out one H plus. So you could imagine a situation like this, where if we do my eraser, that as you drop it in, you end up eliminating one of these guys. And then the concentration drops of H pluses, therefore conversely your hydroxides pick up, and you start to gradually go higher, but you're still going to be acidic. Right? And drop more in, and eventually, there you go, and a little more in, and eventually, in this case, you get down to a few left, and then you would eventually be, this would be considered a neutral solution. So if you go up here a little bit, you would say a pH that is right around 7, and this would be right about here. At some point, all your acid will be gone, and the only thing left will be your salt. Okay, so every time you neutralize this thing, you flip an acid to a base, and so you're going to go from having an acid solution, okay, to having a base solution. Okay, acid solution to a base solution. So in every single acid-base titration, you get a dramatic swing of pH. And if you're doing a strong acid versus a strong base, you'll get a significant jump here. Okay, because as soon as you eliminate all of this thing, all your salt, and when I say a strong acid versus a strong base, I would be like HCl plus NaOH would yield NaCl plus H2O. So when these things react, I'm dropping NaOH in. This guy is a strong acid. This is a strong base. So this is neutral. This is neutral. My salt is neutral. So as soon as all of my H pluses are gone, okay, as I remove them all, only thing left is my NAs from the hydroxides and the Cls from the original H hydrochloric acid, the original acid. All the H's are gone, the Cls still remain. At the equivalency point, only thing left is the salt. And at this point, that salt is neutral. So at that point, you'd be right here. Okay? Right here. Your equivalency point, cut across, that is your pH. This is the number of moles of acid you've added to get to that point. So you may not know how many moles of acid are in here, or were in here originally, but you know how many hydroxides you've added, and they are going to be equal at this point. Okay? For every hydroxide you added, there was one H plus in there originally. Now, if you are titrating with a weak acid, okay, let's say, for example, we have some vinegar in here. Okay. Now, the vinegar is going to be HC2H3O2 minus. Okay. Now, this is a weak acid, and when I react it with my hydroxide ions, it will be forming water, which is neutral, and C2H3O2 negative. Okay, this is a weak acid. This is going to be a weak base. Again, you do have a switch from an acid to a base. So when you're tracking this pH, all right, pH is going to be here, and your POH will be right. Sorry, that would be the moles of base added. Okay. So we have our solution here, and I'm just going to put down HX in this solution just so you To write out the entire thing every time, but we have H plus and X negative, and H plus and X negative, and some of them, because it's a week, it's still together. Most of them are still together. Okay. So as I drop this in, okay, again, I am acidic. I'm going to start adding in my hydroxide. I will start neutralizing some of these guys. Now, again, for every hydroxide I add, I neutralize one of these guys. So I could cross them out, or I could simply erase them. I'm just going to simply cross them out with a different color. So as I add the hydroxide, I knock out one of my H's. And again, I am acidic still. This is basic. Every time I knock out one of my H's, I leave an X negative behind, which is basic. Knock out this H. Okay, I have this guy here. Even though these are weakly basic, the H is really dominant at this point. I'm only slightly increasing. And then at this point, knock another one out, and I go up a little more, and then knock another one out. There's that guy right there, and I have this guy left here. Again, knock another one out. I have HX here, and knock another one out, and eventually, as soon as all my acid is gone, I will have a smaller transition into this guy. Now this pH would have to be like 7 right here, and my equivalency would be probably right about here, and that would be probably around 9ish. But this would be, it's a little harder to tell, where my biggest source of change. Now again, every time I added a milliliter here, I had a certain small change, and all of a sudden 1 milliliter it gets massive change. This is where you're going through your equivalency point, and this is your moles of base you added, and that number of moles right there equals your moles of your unknown acid. Okay. All right. So how do I mathematically complete my titration? All right. What you're going to do is you have your unknown substance. Okay. You set your burette up. Okay. I'm going to flip back to a different color here. All right. You have your burette. Now, whether you use a pH meter or not, I'm just going to explain how you do this. Okay. You got your burette and you have your beaker below. Okay. You're going to do, let's just say, 3 trials. Your first trial is what we call quick and dirty. You want to understand just kind of where this thing is going to turn. And if I don't give you information about how much of this unknown to take, you might need to do some figuring to figure out, okay, will one burette of my base neutralize all my acid or not? So that's something to think about. Now, either way, let's just say you're taking a certain amount and you do your first trial of your start to neutralize. Every single trial should have a certain amount of data that's going to be collected. Okay. The first one is you need to know this guy. Okay. My options for calculations here. Okay. Well, in this case, if it's a liquid, you'd want to know the volume. Okay. So the unknown volume. You should have that for each and every one of these. Okay. And then for every titration, T1, T2, T3, you're going to have a start, you're going to have an end, and you're going to have a change in volume. Okay. Then for every one of these trials, we have one more calculation. So I'm going to do the titration calculation. And you're going to have 3 of these. Now, every single time we try and determine an unknown, you need a known to compare it to, or some scale to compare to. For this particular titration, I usually set a table like this with a known versus an unknown. My known is what's in the burette. Again, it's molarity equals moles per liter. And my known has a known molarity. You can put it in here. So I should know at this point the milliliters, the volume of this guy, okay, the volume, that is going to go right here. Okay, and it has a known concentration as well. You will then use molarity equals moles per liter to find this guy. It should equal this guy, the moles of the unknown, because you titrate to the equivalence point. Now, it might be needing a stoic ratio to flip from one to the other one. Now, you'll see here in this thing that every one hydroxide neutralizes one of these guys. So it's a 1-to-1 ratio. And for acid-base, it's usually 1-to-1. But if you get into more oxidation reduction reactions, you might have it equal at a 2-to-3 ratio, or 2-to-4, or 2-to-5, or some other ratio. So be cognizant of your particular chemical reaction. Once you find your moles of your unknown, you can do whatever you want with it. You could, with this given volume right here, okay, you could find the molarity, which is pretty common. Or you could take this moles and just convert it to mass, if you know what it is. That's another common thing. You could also take the moles of this thing and find molar mass. Different experiments call for different things. If you want to find the molar mass of your unknown, you would need to know first of all, two things. You need to know the mass per mole. So mass of the substance divided by the moles of the substance. So you take this moles, if you happen to know the mass of it, you could then take it, put it right there, and divide the two to get your molecular weight. Very common. A lab is usually, we do a lab of this every year. Okay. For the most part, that concludes our calculations on the titration.